In this lecture, we will start with nodal analysis, and later in this section, we will talk about mesh analysis. Nodal analysis provides a general procedure for analyzing circuits using node voltages as circuit variables. Choosing node voltages as circuit variables instead of element voltages is convenient and reduces the number of equations. We will talk about nodal analysis in two broad cases. So in first case, we will consider the cases which do not contain any voltage source. And in second case, we will talk about circuits which has voltage source as well. Alright, let's talk about steps which we need to follow in nodal analysis. So let us assume that we have n number of nodes. So let me just write it over here. So we have been given n nodes in the circuit. So in the first step, we need to select a reference node. In most of the cases, we need to select the reference node which has zero potential or the least potential in the circuit. So any node which has zero potential or the least potential will be taken as the reference node. In step 2, we will assign voltages V1, V2, V3 and so on to remaining n-1 nodes. The first node is taken as the reference node, and for the remaining n-1 nodes, you need to assign V1, V2, V3 and so on. These are called the node voltages. Next, we need to apply KCL to each n-1 node. So this step is really very important. We need to apply KCL to each n-1 node. Then in step 4, we need to apply Ohm's law to represent branch current in terms of node voltages. We know that current always flows from a higher potential to a lower potential. Let's say the higher potential is V higher and the lower potential is V lower. By Ohm's law, we can say that current, that is I, this is equals to V higher minus V lower over the resistance. This is the branch resistance. So this is the higher node voltage and this is the lower node voltage. V higher minus V lower over R. This will give us the current. Alright. In step 5, we need to write all the set of simultaneous equations, and we will see how we can form all these equations. So in step 5, we need to write all the simultaneous equations, and in step 6, we need to solve all these equations using various methods. And we will talk about all these methods when we solve some problems. Alright, so these are the 6 steps which we need to follow in nodal analysis. Let's apply these methods in this very simple circuit given over here. So we have two current sources. Since we are considering case 1, so there is no voltage source in this circuit. We have two current sources, I1 and I2. We have 3 resistance, R1, R2 and R3. We need to apply all these 6 steps in this circuit. Alright, so let's try to solve it. Before that, I'll quickly change the color. Yeah. So see that the first step is to select the reference node. So before that, let me just mark all the nodes. So these are the nodes we have in the circuit. And I'll take this node right over here as the reference node. So this node is taken as the reference node, and all other voltages will be calculated with reference to this reference node. Alright, let's apply step 2. So we need to assign voltages V1, V2, V3 and so on to all the remaining n-1 nodes. This node right over here, I can say that this is voltage V1 and this is voltage V2, and there are no other nodes in this circuit. This node and this node are same, so there is V1 voltage and this is V2. So in step 3, we need to apply KCL to each n-1 nodes. To apply KCL, before applying KCL, we need to mark all the branch currents. So I1 is coming to node 1, and let's say this is small I1 and this is small I2, and from R3, I3 is flowing. So we have small I1, small I2 and small I3 as branch currents. So let's apply KCL at node 1. So I'll quickly write over here KCL at node 1. See that I1 is entering node 1 and I2 is leaving node 1. Small I1 and small I2 are also leaving node 1. So I can write it as I1 is equals to small I1 plus small I2 plus capital I2. So let's say this is equation 1. Alright, let's apply KCL in node 2. So I'll quickly write over here KCL at node 2. Let's see what we have. We have capital I2 entering the node. small I2 is also entering the node, and we have I3 leaving the node. So I can write it as small I3 is equals to capital I2 plus small I2. And let's call it equation 2. Alright, so we have applied all these 3 steps. Let's apply step 4. So in step 4, we need to use Ohm's law to represent branch current in terms of node voltages. We can represent I by V higher minus V lower over R. So let's consider this circuit. We have I1 is equals to V1 minus 0 over R1. See that 0 is taken as the reference voltage because this is the lowest potential over here. That's why I have taken it as 0. So V1 minus 0 over R1, this will give us I1, and I can write I2 as V1 minus V2 over R2. See that we have arbitrarily assumed the direction of I2. If in case I assume the direction of I2 from right to left, then I can write I2 as V2 minus V1 over R2. Alright. So current always flows from higher potential to lower potential, and we can assume any direction of the current. And in the final result, if current comes negative, then it will be clear that the direction of current which we have assumed is reverse of the original direction. Alright, so let me quickly delete all these values. So now we have I3 as V2 minus 0 over R3. Let's substitute all these values in these two equations over here. So we have capital I1 is equals to small I1, and this is V1 over R1, plus I2, this is V1 minus V2 over R2, and plus capital I2. Similarly, we have V2 over R3 is equals to capital I2 plus V1 minus V2 over R2. Alright, so these are the two equations which we have. Now in the previous sections we have already discussed that 1 over resistance is conductance. So 1 over R1 can be written as capital G1, 1 over R2, this can be written as capital G2, and 1 over capital R3, this can be written as capital G3. Let's substitute the values of 1 over R1, 1 over R2, and 1 over R3 in these two equations over here. So we will have capital I1 is equals to V1 G1 plus V1 over R2, this can be written as V1 G2, minus V2 over R2 can be written as V2 G2 plus I2. Alright, and in the second equation, this can be written as V2 G3 is equals to capital I2 plus V1 over R2 can be written as V1 G2 minus V2 G2. Alright, so let's call it equation 3, and this is equation 4. Alright, so I'll quickly combine all the current terms on one side and rest of the voltage terms on the other side. So this can be written as I1 minus I2 is equals to V1 times G1 plus G2 and minus V2 G2, and the second equation, that is equation 4, this can be written as I2 is equals to V2 times G2 plus G3 minus V1 G2. Let's call it equation 5, and this is equation 6. I can write these two equations in the form of matrices. Let me show you how. So I can write it as G1 plus G2 and minus G2, and in the second row I can write it as minus G2, and here G2 plus G3. So this is the first matrix, and here I'll write V1, V2, and then we have I1 minus I2, and in second row we have I2. Alright, so this is a matrix notation of both of these equations. We can solve these equations using various methods like substitution, elimination, or we can solve these matrices using Cramer's rule. That's all for this lecture. Let's have a quick recap of whatever we have covered in this lecture. So we started the case 1 of nodal analysis. We have 6 steps to solve any circuit using nodal analysis which do not contain any voltage source. In the step 1, we will select a reference node, and generally this is taken as the node which has the lowest potential. In step 2, we will assign V1, V2, V3 and so on all the voltages to n-1 nodes. In step 3, we will apply KCL to all these nodes, and in step 4, we will use Ohm's law to represent branch currents in terms of node voltage. In step 5, we will form the simultaneous equation, and in step 6, we will solve all the equations which we have in step 5 to get the value of voltage and current. Alright, let's try to solve a couple of problems in the next lecture.